Hello again. Is it better? Okay. So this lecture I'm supposed to talk about overconvergent modular symbols, which means I'm supposed to introduce the notion of p-adic distributions, and we're going to replace the sim-k spaces that I was in the last lecture with these big Banach spaces of distributions. Before doing that, I thought I would give sort of a little bit of a motivating example from overconvergent modular forms rather than overconvergent modular symbols, and just tell a little story about p-adic families. So let me do that and then come back to modular symbols. So let me start with some p-adic families. And this theme will be picked up again in the last talk when we talk about families of modular symbols and two-variable p-adic L functions. So let me look at weight k cus forms, let's say of level n, and then I want to put this upper ord. This I mean the space of ordinary forms. So this is let this denote the space of p ordinary forms. So some prime p is fixed here. And what does p ordinary mean? So this is the eigenvalue. And as I'm looking at this, I think I want p to divide n. Well, let me just put a p there so I don't. That's a p. So now p should not divide n. So I fix some prime p, and I'm actually going to look at level pn, where p is exactly dividing the level, and then p ordinary means that the eigenvalue of up is a unit. So that's the AP is not divisible by P, just like for an elliptic curve, it would be an ordinary elliptic curve. So if I look at this space, here's the following amazing fact about it. The fact, the dimension of this space, so the space of ordinary modular forms, only depends on k modulo P minus 1. So as I vary through all k's in a fixed residue class modulo P minus 1, that space has the same dimension. So for example, so here's an example. Let me take cus forms of level 15, P equals 3. So I'm going to look at even k. Otherwise things would be vanishing. So I just want to look at the even k. So then the condition of k modulo P minus 1, that's kind of vacuous here. This is one-dimensional. And if I look at its unique normalized new form, its Q expansion looks like this. Copying out of my notes. Okay, so I'm picking P equals 3, so in particular, it's ordinary at 3 because the third coefficient is minus 1, so 3 doesn't divide it. So this is ordinary, so the full space is ordinary, and then the fact, well, let me just... So this fact about that the dimension of the space is independent of the weight. So this fact implies that the dimension of sk gamma naught of 15, ordinary part, is 1 for all even k. And that's a bit of a phenomenal statement because as you vary k, let's say k increases, those spaces get larger and larger. Right? The dimension of sk of any fixed level goes off to infinity. Sk goes to infinity. But if you go to Sage and you ask it, compute for me the level 15 modular forms of weight 8 and some like big dimensional space, and you look at all of them, they're all non-ordinary at 3 except for one of them. So there's only one form that's ordinary for every single weight. And even better than that, so there's more. So moreover, if I, so let me say, so let f sub k denote the unique normalized form. Ordinary form. So if I look at fk and fk prime, these will be congruent mod, let's say 3 to the n, when k and k prime, I guess how I'm normalizing this, are congruent mod 3 to the n minus 1. All the weights are even. So it's saying as I bring the weights closer and closer to each other p-adically, then the Fourier expansions, that's what I mean by this congruence here. So the Fourier coefficients of those two forms get closer and closer 3-adically. So that's a p-adic family. It's parameterized by some integer k, and as I move k along kind of the p-adic world, as things get p-adically closer, then the modular forms get p-adically closer. So this is Hita theory. Things are ordinary here. This is Hita theory. And the fact that I stated at the beginning that the dimension of the space of ordinary forms is independent of the weight is what lets this work in some sense. What Hita does is he interpolates, so Hita kind of interpolates the spaces S, K, gamma 0, NP, ord as K varies. Somehow makes a big space over weight space that sort of encodes all of those spaces together. And that's plausible because they all have the same dimension. So you have some object that like puts them all together. And you clearly can't do this in the non-ordinary case, because in the non-ordinary case, the corresponding fact can't be true because the whole space blows up in dimension and the ordinary part is stable, and so the non-ordinary part has to be blowing up in dimension. And so clearly, this can't be true for all forms. This dimension of the SK goes to infinity. SK goes to infinity. Okay, so this is supposed to be somehow like a beginning of motivation as to where these spaces of distributions might come from. It's a little bit of a shaky motivation, but I'll still state it anyway. What was done by Coleman to get around this problem, so Coleman ultimately generalized Hita theory and made families of modular forms even if they're not ordinary. So what Coleman did, so Coleman replaced, well, let me just look at all modular forms, MK, I should say this as simple, so gamma naught will be gamma naught of NP, just to save me some writing. So replace this space whose dimension varies with K with, I'll call M upper dagger K gamma naught. And this is the space of overconvergent modular forms, whatever that is. And this is some infinite dimensional space. And so properties that it has, so classical modular forms sit inside it. So it's just an enlargement of that space. Moreover, if you're handed a random overconvergent modular form, there's nearly a theorem that lets you test whether it was classical or not by its eigenvalue for UP. So if F is some overconvergent modular form with small slope, so the slope is just the valuation of the eigenvalue at UP. And I'll talk more about this later on. I don't want to go into it right now. Then F is classical. And this is a very vague statement, but Coleman interpolates these spaces. Over weight space, p-adically. And the fact that Coleman took this sort of nice, beautiful space of modular forms, classical modular forms, and blew it up to this infinite dimensional space, at least got around the problem that as you try to make the family, the dimension doesn't get constrained anymore because everything's infinite dimensional. So that's the weak motivation that I'm giving. We're going to pass from sim k, which is this space whose dimension depends upon k, to some big infinite dimensional space who's always infinite dimensional. Okay, so this is the modular symbol analog. So recall what we did last lecture. Modular symbols. So that's the notation I was using last lecture. Remember, VK means sim k of C squared. And by Eckler-Shimura, this corresponds, not writing things exactly, but to modular forms of weight k plus 2, same level. And we will, following sort of Coleman's lead, is replace VK with, what am I calling it, DK, some infinite dimensional space of distributions. And dk admits a surjective map to vk. That's going to be the analog of this one here. So once you have a surjective map, then I can push forward modular symbols. So I can, is it going to be space? Yeah, I think I can squeeze that in. I could look at modular symbols with values in dk. This is going to be the space of overconvergent modular symbols. And then I can just map them to classical modular symbols. So called specialization. This is elements here, simply functions from delta 0 to dk, and so then I just use that map and push them forward to functions on vk. Things are a little bit dual here from the previous situation. There, modular forms are a sub of overconvergent modular forms. Here, classical modular symbols are a quotient of overconvergent modular symbols. But that'll be the game plan. And considering I just said that, I should also say that the way I introduced modular symbols in the last lecture is maybe dual to more standard notions. Like maybe how it's programmed on Sage and other places, a modular symbol is the paths in the upper half plane with coefficients somewhere. The way I talked about it, they were just functions on the paths. So they're just dual to each other. Maybe that's part of explaining what's going on here in terms of inclusions or surjections. Okay, so is that okay? How was the motivation? So now the next step is to just write down these distribution spaces. And they're not so bad. So let's do distributions. So distributions are dual to functions. They're supposed to take in as functions as inputs and spit out numbers. So first let me write down the spaces of functions, and then we'll dualize those spaces to get the spaces of distributions. So here's the nice space of functions we'll be working with. Let bold A be convergent power series on the closed disk, on the closed unit disk of CP. And I'm not writing it, I guess I'll write it over QP. Everything in my mind is going to have coefficients in QP. So this is some actually quite concrete thing. These are power series, so there's some AN, Z to the N. These ANs are in QP, and to say that a p-adic power series is convergent on the closed unit disk is just the condition that the coefficients tend to 0. Because I'm on the closed disk, and so let's say I plug in 1, then I just get the sum of the ANs. Remember that it's p-adic, so sum converges if and only if the general term tends to 0. So as long as those ANs go to 0, that suffices. That's exactly what it is. And this is a Banach space, so A is a Banach space. Here's a norm. The sum of AN, ZN, its norm is going to be just the max of all the norms of the coefficients. Like these coefficients go to 0, and so there's the biggest one. So just take the size of that. That makes it into, it's complete under that norm, so it's a Banach space. And then I can dualize. So D, this is going to be my space of distributions, are the continuous homomorphisms from A into QP. And that's again a Banach space under the dual norm. And just for some notation, I should get this up there now because I just do it instinctively. If I take a distribution and a function, well, by the very definition, I can plug f into mu. Right? So this makes sense, mu of f. But we want to kind of inspire a sort of functional analysis thinking. So I'm not going to always write it like that. I'll also write it like this, the integral of f d mu. So that's just the definition. If I write something like this, an integral, there's no real integral there. It's just, it means that. We'll think of that as an integral. Maybe there's secretly an integral there. Right, so I have this promise to try and pretend that everything is really concrete. I mean, try and convince you that everything is really concrete. And so let me do that here. These actually are not such outrageous spaces at all. So one can really describe distributions, and I'll do that via their moments. Let me explain what I mean by this. So first, let me point out that the span of the monomials say z to the j is dense in A. That's just saying that I can approximate anything in A arbitrarily well by a polynomial. And the coefficients of A tend to 0. So I just take enough terms, and then what's left over is really highly divisible by P. So that means, so if they're dense, that means that a distribution is uniquely determined by what it does on them. So I can just plug in all those powers of Z into the distribution. That gives me a sequence that completely describes the distribution. So I then get so this means mu in D is uniquely determined by the sequence mu of Z to the J, as J goes up through all the terms. And so then I get a map. So D embeds into the product of all the QPs over all J, one slot for each moment. So this is just rewriting it. Let's go to, say, the sequence of moments. And in fact, it's easy to describe the image. Not every sequence arises. The sequences that arise are exactly the bounded ones. So in fact, the image equals the bounded sequences. And let me at least check one direction of that for you, meaning if I give you a bounded sequence, then there is a distribution that maps to it, and it's not hard to see that every image is in fact necessarily bounded there. So, so take any bounded sequence, say alpha n, then I want a mu so that mu of Z to the J is alpha to the J, no, alpha sub J. That's my bounded sequence of moments. So I want to say there is a distribution whose moments is that. And so, well, I'm going to define mu on any element of A. A random element of A looks like this. A n z to the n, where the an's go to 0. And I'll define that to be the sum of an, alpha n. And because the an's are going to 0 and the alpha n's are bounded, the an's alpha n's are going to 0. So that sum converges. So that makes sense. And I'll leave the other half for you to check. So from the point of view of these, just forgetting all the other structures, the fact that it's power series ring, you can multiply power series and things like that. Just thinking about the moments and the coefficients, this space D, this is just in correspondence with bounded sequences in QP, and the space A is just sequences in QP tending to 0. That forgets the rest of the structure, but that's what they are, what their underlying spaces are. So that's supposed to be my concrete description of the distribution spaces for you. It's just sequences that stay bounded. But to define modular symbols with values in D, you need a matrix action on everything in sight. Otherwise, it wouldn't make sense. And the matrix action doesn't come from this description by sequences. We have to go back and remember where they came from as dual to power series. So let me define for you the matrix actions. And I'm going to write down a funny group that acts. I'm going to call it sigma 0 of P. Let me write it down, and then we can talk about it. So these are matrices in N2 of ZP such that A is a unit and P divides C. It's a semi-group, I guess. The problem with these distribution spaces is that SL2Z doesn't act. You're going to need to have P dividing the lower left, the C. So that's going to be required. And so that's the position I'm putting here. But we want a group bigger than gamma 0 of P that's acting because we want the Heck operators to act. Remember how the Heck operators act? They act by those matrices 1A0P. And just the condition we're putting here, at least those matrices 1A0P, they're all in here. And there's the other matrix P001. That's not here because we're at level with P in the level. Right? So it's TP becoming UP, so that one's gone. So at least all the Heck operator matrices are in here. And in fact, this will turn out to be like the largest group that acts on these distribution spaces. So that's where it's coming from. And let me tell you the action. So it's going to be a weight K action. So let me fix some integer K, non-negative. Let me pick one of these matrices of this form, ABCD. Let me take a function. And then I'm going to tell you how gamma acts on F. This is the weight K action. So dot with a K underneath it to indicate the K action. So this should be another power series. And here's the formula. Like this. So this is this automorphic factor that's common with modular forms, and then F of some linear fractional transformation of the variable Z. And note that it's not the kind of standard thing that you might see. It's not AB plus C over C plus D. That's because this is a left action. Right? Modular forms are, the matrices act on the right because you're acting on the variable on the left. In part, I think everyone really likes to see AZ plus B over CZ plus D. And you like it so much that you put it on modular forms, you insist on a modular form so modular forms become right modules. Because if you act on the variable on the left, then you have to act on the space on the right. And so maybe that's why everything's going haywire here in terms of normalizations. This is a left module. I'm acting on the left, so I have to act on the variable on the right. So that action is thinking of things as a row vector and then multiplying on the matrix on the right. So that's where that action is coming from. And the reason I'm doing it this way is that I'm going to dualize, and then I'm going to get a right module. And we wanted right modules for the modular symbols. So I'm going to dualize and use the dual action. So now, dually, if mu is in D, and now this is a really simple action to write down, I define the weight K action on the right, and I'll denote that by a slash with sub K. Well, that's a distribution. Well, to define that as a distribution, I have to tell you what does it do to a function. So let me plug in a function. And this was a definition. This is a definition. I just act on the function using the weight K action. Now that's a right action. And then when I'm thinking of these things as modules with the induced weight K action, I write A sub K and D sub K. When this is the group, this is the way that I'm acting. So here's the difference that's occurring is that when we were varying the weight for classical module symbols, we changed the module, we changed sim K, and then this is the space whose dimension kept varying. Now we have one space of distribution, and it's the same underlying space, but we're just changing the action on it. And that's supposed to be interpolating all the different actions that we've seen so far. Okay. Because I haven't written it down yet, so let me just write this down now. So we consider gamma 0, delta 0, dk. Remember, gamma 0 is gamma 0 of np to be the space of overconvergent modular symbols. I'll call them OMS of weight k. And now I want to say that this relates to classical modular symbols. So that's it's a specialization map. This is what I promised you at the beginning, that this big Pollack space should emit a surjective map to sim k. If I can write that down that map, then I can take a big symbol here and push it down to a sim k symbol. So I'll just write down this map for you. So rho k is going to be the map from dk to vk. Well, vk is, okay, actually, so vk was sim k of c squared. I don't want c, right? I'm now in a completely chaotic world. So I should write, let me do this, vk of qp. And this will mean sim k of qp squared. And now whenever I write vk of something, it'll mean just plug that thing into the sim k. And here's the map. I take my distribution mu, and I map it to, okay, the integral of y minus zx to the k d mu. And what does this mean? Remember, the integration is just formal, and in fact, those x and y's are just formal placeholders. It just means binomial expand it out and integrate each coefficient. So literally what this means is you sum from 0 to k of k choose j. I guess I want to do it this way. Minus 1 to the j, then I should have a z to the j on the coefficient x to the j. So I'm looking at mu of z to the j, x to the j, y to the k minus j. Right. And this mu z to the j, that means the integral of z to the j. Just plugging it in. And amazingly, this is sigma naught of p equivariant. Meaning I could act by matrices here and then specialize, or I could specialize and act by matrices and I get the same answer. So sorry, I'm not saying much more about where that formula comes from, but it's the formula that makes that work out perfectly. And you needed this equivariance for the action of the matrices, otherwise modular symbols wouldn't push forward. Because you're asking things to be invariant in the action of gamma. If I push them forward and it's not compatible with the matrix action, it won't be invariant for gamma anymore. Oh, at least I can check this when k is 0 in the weight 2 case. Then it's why not write that all down in the weight 2 case? Then things are really quite easy. Yeah.
Am I mistaken, or did you want me to find an action of sigma naught?
Well, gamma naught's inside of sigma naught. Yeah, so gamma naught of NP. So the lower left-hand corner is divisible by NP, so you have the condition that P divides C, and the determinant is 1, which forces A to be a unit. So that's, yeah, this is a larger group than this one. Okay, so example. So k equals 0, which means weight 2. This the shift by 2. Then, so this row 0, so that this is a map now to V0, which is just QP. I still have that complicated map up. That just becomes mu goes to mu of 1. So it's like the total measure. You're plugging in the constant function. So it's like taking total measure. And that is equivariant because if I take mu and act by gamma and then plug in 1, the definition is, well, you act by gamma on the left on 1, and that's the same as, well, gamma acting on 1 is the constant function, so it stays constant. So that's again gamma of 1, but QP is a trivial module, so that's the same as acting by gamma afterwards. So I can pull the gamma through. So that's at least a check in weight 2. And then once I have this equivariant map, so this induces this back to general case, let me call it rho k star. This is the specialization map on overconvergent modular symbols. I guess I have to write all that out. So this here is the space of overconvergent modular symbols, and now this is the space of classical modular symbols, except that I'm thinking of them having QP coefficients rather than C coefficients. They're defined over Z, so it doesn't matter what field I really put there. And this space we understand well, right? This by Adler-Schmür is a copy of modular forms plus a copy of Cust forms. This space presumably is enormous, right? This is some infinite dimensional space. There's probably lots and lots of things here. In fact, this is also an infinite dimensional space. So one doesn't hope that this is an isomorphism at all. This should be compared to the situation with overconvergent modular forms, when modular forms are a sub of overconvergent modular forms, and the ones of small enough slope are classical. And so there should be some sort of theorem like that. If I restrict to how big of an eigenvalue UP acts on this space, then maybe it can become an isomorphism. So that's what's true. So this is what we call specialization. And I want to cut out for you a subspace of the source on which this map becomes an isomorphism. And to do that, I have to talk a little bit about slopes of modular forms, as I promised before. So, slopes of modular forms. So back to this classical situation, I have a weight k form on gamma 0, an eigenform. And let me say f acted on by up is lambda f. So lambda is AP. I'll just use the notation lambda. Then the definition of the slope that I keep saying, so the slope of f is just the p-adic valuation of lambda. This is p-adic valuation. Where I'm normalizing this ORD p function to be ORD p of p is 1. ORD p of a unit is 0, like ORD p of the square root of p is a half, something like that. And so the bigger the slope means the bigger the valuation of the eigenvalue of up. And here's a fact, that's what I want to say. I should say ordinary, the definition of ordinary before is slope 0. Right? That means it's a unit. And here's the fact, is that for any such f, one of these eigenforms, the slope of f is less than or equal to k minus 1. And I'll justify this for you, at least partially, in a moment. But it's a little bit of a weird fact because the left-hand side is a p-adic thing. So, what's the p-adic valuation of the eigenvalue of up? Where the right-hand side is like an Archimedean thing. It's an inequality. It's an Archimedean inequality. And so, saying if I have some fixed weight, then that, weight 100, then somehow the slopes can get no bigger than 100. And so if I go back to this specialization map, it's really on both sides. I always thought it was just there. Okay, either way you look. If I look to here, then let's say k is 100. So this space can't have any slopes bigger than 100, but this one can. This one can have arbitrarily high slopes. So what you want to do is just cut off at that point, cut off that boundary point. And so that'll be the idea. But let me first let's say a few words as to why this is true. Here's the reason. Well, there's two cases to consider. If I have a form on gamma 0 of np, so p is in the level here exactly once, it's either p nu or it's not p nu. So those are two cases. So it can be p nu. And then here's something I'll just pull out of the air. Just when you have a p nu form, then you have almost an exact formula for the, I guess, the lambda in this case. Well, that's the AP. That's just up to sign. It's p to the k over 2 minus 2. It's the power of p up to sign. That's not right. Minus 1. Yeah, that's right. So when you're weight 2, then that's just plus or minus 1. And that's the fact that you know from elliptic curves that, like, if you have multiplicative reduction, then your AP is either plus or minus 1. So that's the generalization of that fact. And note that k over 2 minus 1 is less than k minus 1. So this case is done. Then there's the other case, your p old. So if your p old, the theory of new forms tells you that there exists some form g on gamma 0 of n such that f is in the span of g of z and g of pz. And right, g is naturally a form on gamma 0 of n, but I can just think of it as a form on gamma 0 of np. And g of pz naturally lives on gamma 0 of np, and I look at their span, and it's a very pleasant little computation to do. Just with Q expansions, you could see that UP preserves that space, that two-dimensional space. And if you write down the characteristic polynomial of UP on that space, it's just the familiar Hecke polynomial, x squared minus APX plus p to the k minus 1. And that tells us the claim, because the eigenvalues of f are the roots of this polynomial, and they're integers, and their product is p to the k minus 1. So the valuation can't be any bigger than k minus 1. So this implies that the valuation of the roots is less than or equal to k minus 1. And note that this extreme value of k minus 1, this is what's called critical slope, it only occurs in one special case. If one of the roots has exact valuation k minus 1, well then the sum of the roots is AP. So then if one root has all its valuation k minus 1, the other root's a unit. So then their sum is a unit. So that means AP is a unit. And so that means that your form has to be ordinary, this form G. So when you have this form G, if it's ordinary, you can kind of what they call p-stabilize it in two different ways, depending on which of the two roots of this polynomial you pick. You can pick the ordinary root, you get an ordinary form, or you can pick the critical slope root, the one of slope k minus 1, and then you get this critical slope form. That's why it's less than or equal to. That's the only case the equality happens. And let me just say in words, Coleman's theorem that I stated at the beginning of small slope forms being classical precisely said is if your slope is strictly less than k minus 1 and you're overconvergent, then you're classical. And it's true that there are overconvergent forms of slope exactly equal to k minus 1 that are non-classical. So this critical slope is a weird boundary case. Sometimes you're classical, sometimes you're not. Everything bigger than k minus 1 is purely overconvergent, not classical. Everything less than slope k minus 1 is classical. And we'll see the exact analogous picture with modular symbols. Okay, so what I need to say, let me fix a real number, h, and let me define m upper less than h. I'm trying to cut off the part of h where up acts with some bounded slope. So this is just the subspace of m where up acts. I should say what m is. M is a Hecke module. M is going to be the space of overconvergent modular forms, or just modular symbols or classical modular symbols. So the space of m where up acts with slope strictly less than h, which is something that one can make sense of. If m was a finite dimensional space, you break up m into the generalized eigenspaces of up, and you look at the eigenvalue of up, and if the slope is less than h, you put it in, and if it's not less than h, you throw it out. And there's an analog of that for infinite dimensional spaces. And so here's the control theorem that Glenn proved that compares overconvergent symbols to classical ones. So I'll go back to the specialization map. So I write down the space of overconvergent modular forms, and then, modular symbols, and then the space of classical symbols. And, sorry, I'm not going to write the QP. I hope you know. Yeah, I already put the parentheses. Too late. I mean QP here. And I put this map. Now if I restrict, oh my gosh. Okay. I'm sorry, this is k. So the slope is less than k minus 1. So I was about to write less than k minus 1 here and less than k minus 1 here. Except that now my k is off by 2. Right? So the weight is k plus 2, and so then this inequality should say k plus 1. So then I should write less than k plus 1. Less than k plus 1. And then that's an isomorphism. That's the statement of the theorem. And just like for overconvergent modular forms, if I put exactly equal to k plus 1 there, there's a problem. It's not an isomorphism in some cases. That's more dicey, so I'm not gonna touch on that issue at all. Yeah, so let me just put in print that this is the analog of Coleman's theorem. Small slope implies classical. So that's the comparison between overconvergent and classical. And here's one neat application. Let me just begin it. So let me take some, again, a cuspidal eigenform of weight k. So from the first lecture, I can attach its modular symbol. It's a classical modular symbol. So this is something that's in Hom delta 0 into vk of c. And just like the example I did with x naught of 11, modular forms of level 11, Uh, that's right. Okay, I'll just do that. Oh, that works great. Thanks. Thanks. Actually, I'm being a little sloppy here. Let me. I'm going to assume for simplicity that if I take my modular form and I write its Q expansion like this, then these ANs, they live in some number field, and I'm going to embed that number field into Q bar in some way, and then I'm going to embed that Q bar into QP bar, and I'm going to assume that the image of all the eigenvalues is in QP, just for simplicity. So let me assume that all the ANs are actually lying in QP. So that just says that you take the field generated by the Fourier coefficients that P splits completely in it, or more so that there's a prime of degree 1 over a prime in my embedding of Q bar into QP bar. But this is just to make the notation a little bit easier. And, well, it's not making anything easier. What? I have a better idea. I'll just lie a little bit, and then we'll sort of say what I'm lying about. This is what I wanted to say next. I'll just write it down. Okay. So phi f. So rather than psi f, I'm going to write phi sub f plus or minus, and this is going to be defined as psi f plus or minus modulo some complex periods, like this, omega f plus or minus. And these are supposed to be like the period lattice that I wrote down in the original example. And now I'm going to say that this takes values in vk of, and this is what I didn't want to know what to write down here. And apparently my notes, I wrote down qp bar, so that seems fair enough. QP bar. So when you mod out by this period lattice, what happens is the values you get become algebraic. So there's something in Q bar, and so I just embed Q bar into QP bar, and then so I'm all the way up here. But in fact, I'm in some finite little extension of QP. Maybe I'm just in QP with some simplifying assumptions. And then I define phi f to just be the sum of these two symbols. Okay, so here I just somehow made something that's p-adic now, rather than complex. Let me put that here. Basically, that's just some normalization issues. Attached to my modular form, I can get a nice modular symbol. And then by the control theorem, I should assume that the slope of f is less than k plus 1. So now I'm in the range where this modular symbol, this phi f, is here, meaning has slope less than k plus 1. So I can uniquely lift it to a symbol here. So let me do that. By the control theorem, there exists a unique phi sub f, a Hecke eigensymbol, lifting little phi f. And then here's the second theorem that I wanted to state. This is relatively simple if you know the definition of all the objects, but it's still kind of striking in its statement. So I take this overconvergent modular symbol phi f. This is now a map from degree 0 divisors into distributions. I plug in this particular divisor. And remember, the very first thing I said in my talks is that when you take the classical modular symbol and plug in that divisor, you get the L value at 1. Now what you get is the p-adic L function of the modular form as a distribution. So this is the p-adic L function. Nope. So the p-adic L function is a distribution. And so it is the p-adic L function. I'm going to say more about p-adic L functions. I'm going to give in the next, they'll be talked about more. So if you haven't seen it before, it's, well, I'll say maybe now is the time to say things, unless there are questions at this point. And maybe I should point out before talking a little bit about p-adic L functions in the sliver of time that's left, is that try to make clear that this space dk is a concrete space, and in fact you can really compute it like on a computer. You can go and take it as sequences of moments modulo various powers of p, and so you can compute modular symbols with values in dk, and so you can in theory, compute everything in this isomorphism. And so you can make this symbol phi f. And so then you can just really make the p-adic L function. And it gives a very efficient algorithm for computing p-adic L functions. And if you have never seen a p-adic L function before, let me give it, what is it going to be, a 3-minute intro on p-adic L functions. That will run 2 minutes over. Okay, so p-adic L functions. Okay, so let me write it as LP of F, p-adic L function attached to a modular form. This should be some gadget that that knows all of the complex. You take the L series of F and twist it by characters, evaluate at 1. Here, chi is a Dirichlet character of conductor some power of P. So I run through all Dirichlet characters of prime power conductor, and I look at all these L values, and this gadget should know them. And then on the surface, that makes no sense because this is a p-adic object and these are complex numbers. And you solve that just as I kind of muddled through before. You divide by an appropriate period. Now these become algebraic, and then I embed them into QP bar. So at least it's a statement that could make sense, that this p-adic object knows these p-adic numbers. And how does it know it? Well, you kind of change your point of view, and you think of the p-adic L function as a function on characters. Namely, given chi, LPF spits out that number. Well, maybe up to a constant, like some controllable constant, which I'm going to completely suppress. And so what kind of gadget takes in characters and spits out numbers? Well, that's a distribution, right? Because it's taking in functions and it's returning numbers. And so the LPF should equal a distribution, i.e. dual to some nice space of functions. Also, with this much said, that the p-adic L function knows all of these twists. Remember at the very beginning of the first talk, I said that all of those period integrals encode all of those twisted L values. And so the modular symbol attached to the form knows all of those twisted L values. So this theorem here, that the overconvergent lift of the classical modular symbol given the p-adic L function, it's all about the same data. This little phi sub f knows all the period integrals, so it knows all of these twisted L values, and you somehow wrap them all up into one object, namely this thing, the p-adic L function in this case. However, there's a problem, and it's always great to end a lecture on a major problem. So, well, it's not like an unsolved problem, it's just a problem with exposition, that how I have things written down, this p-adic L function is sitting in the space D, which was the dual of A. But this is a problem because what I'm saying on this slide is that the p-adic L function should be putting in things like chi, some finite order character, and spitting out an L value. But finite order characters are locally constant. They're not given by power series. The power series is locally constant, it's 0. So chi is not an A. That's the wrong space to be. So this is, what I've said, nothing is false. It's just in fact that this is in a much smaller space of distributions where you can integrate against more functions. So there's a better space of functions to be looking at. Let me say, script A are locally analytic functions on ZP, which means for every element of ZP, I can find a little neighborhood around that point for which the function is represented by a power series. Since ZP is compact, it only takes finitely many power series. So then, of course, A sits inside of A. If you're a 1 power series, then you're locally represented by a power series. And so then I can make a script D to be the dual of A. And I'm cheating here because I'm not telling you the topologies, but that's fine. There's a topology on it. You take that dual. And this is the world where the p-adic L function should live, this locally analytic distribution, because chi is certainly locally analytic. It's locally constant. So you just take the constant power series to approximate it. And then, here's the last fact that I'll close on to kind of reconcile all these problems. If I look at modular symbols with values in D, I should say, note that D maps to D. Right? If I have, just by restriction, if I want to integrate, if I have a gadget that can integrate all locally analytic functions, of course it can integrate all rigid analytic functions, so I get a map. In fact, this is an embedding, because this is dense. I didn't tell you the topology, so that's easy to justify. So this is an embedding. So I get a map like this. And if I restrict to finite slope subspaces, this is any h, there's no like k minus 1 here. That's an isomorphism. So any Hecke eigens, any overconvergent modular form, which is a Hecke eigensymbol, necessarily takes values in this much smaller space of distributions, these locally analytic distributions. So that makes sense of Stevens' theorem that the p-adic L function is the value of the modular symbol at 0 minus infinity. It's not just a rigid analytic distribution, it's in fact a locally analytic distribution, and then you can integrate against all the functions. So at the beginning of the next lecture, I'll clean up some of these things and justify, well, maybe I will, maybe I won't, why this is true, and then we'll go on to proving the control theorem. Okay, thank you.